We made it to our 6th mission, the last one before the tuning exams. So many applications have been learned thus far, teaching us that spontaneous electrochemical processes are extremely useful. But the Hokage wants our next mission to be about learning when an electrochemical process is not useful, or corrosion. And to do this, we must venture to the land of iron and the hidden corrosion village to learn from the general of the land. Now, the goal of this mission is to gain knowledge about corrosion, an environmental voltaic cell, and understand the corrosion of iron. Now, although other metals like copper and silver, for example, can corrode, our focus will be iron. So see you there, folks. Welcome to the land of iron and the hidden corrosion village. We are received by the general of the land, Mifune, and he wants to make sure we have a great experience and will personally start and end the journey with us. He begins. Corrosion is the natural redox process that results in unwanted oxidation of a metal. The metals are oxidized to their oxides, which means you have a metal or an oxygen compound, and their sulfides, meaning you have a metal and sulfur compound. And this process shares similarities with the operation of a voltaic cell. Now, the rusting of iron is the most common and economically destructive form of corrosion. This means that tens of billions of dollars of damage to cars and ships and buildings and bridges or the steel industry, etc., each and every single year. Now, we often think of rust, but rust is not really a direct product of the reaction between iron and oxygen. It actually arises through a complex electrochemical process based on 6 different facts. And we'll be verifying these 6 facts as we venture through the village. Mifune states, here are some corrosion facts and features. Fact number 1, iron requires moisture for rusting. It does not rust in dry air. Fact number 2, rusting in air-free water requires the presence of oxygen. Fact number 3, iron loss and rust formation happen in different locations on the same object. Okay? Fact number 4, low pH, meaning you have a high concentration of H plus or H3O plus, is going to accelerate iron rusting. Fact number 5, ionic solutions like aqueous salt solutions are going to expedite the iron rusting process. And then finally, fact number 6, iron rusts more quickly in contact with the less active metal, like copper, for example, and more slowly with the more active metal, like zinc, for example. So you can say that rusting requires moisture and, of course, more quickly at low pH in ionic solutions, and when the iron is in contact with the less active metal, to sum it up for your flashcard moment. Again, we will be verifying these facts as we go along. Mifune then states, there are 2 separate redox processes that occur during corrosion. First is the loss of iron, and second is the rusting process. Mifune wants to focus on the redox process during the loss of iron. So of course we know that redox means we need a cathode and an anode. So let's go ahead and picture an iron bar here. So we have this iron bar, then we have a water droplet. Now on this iron bar, we see that there's a little pit, or there's going to be some type of dent on the iron bar. And then over here, we see some rusting happening. So 2 different locations of the iron bar being compromised or damaged in some way. Our focus won't be rusting right now, so we're going to focus on iron loss at the pit here. Now, the pit is really just a strain or ridge or dent that's going to come in contact with water on the iron surface. And that is going to verify fact number 1. So we have iron loss, and a pit is formed, and it becomes in contact with water to create the anodic region. And at the anodic region, we know we're going to have oxidation. And so we can sum it up with this half reaction. We have iron solid is going to lose electrons to form the aqueous Fe2+, that's going to be in solution here in the water droplet. So the electrons are going to move from the iron into reaching a region with high oxygen, which is going to verify fact number 2. And this high oxygen is usually near the edge of a water droplet. At the cathodic region, you're going to have electrons that are released from iron atoms that are going to reduce oxygen. And so the reduction half reaction is going to be our oxygen, 4H+, of course, absorbing 4 electrons to form water. And the pit is going to serve as a separator. Now, the combination of the anodic and cathodic regions leads to the overall corrosion process. As we can see, with the corrosion process directly related to, of course, the loss of iron creating these pits, there is no rust formation, okay? So we want to remember that the pit is separate from rust. This photo is just showing how a water droplet is going to influence iron at two different spots on the iron. Mifune then states, corrosion is a complex electrochemical process that requires both moisture and oxygen, with multiple factors influencing its rate, including pH, ionic solutions, and contact with other metals. He then goes on and says he will have his bodyguard, Okisuki, explain the rusting process and will meet us again later on. Okisuki, Mifune's bodyguard, greets us and begins to discuss the rusting process. He emphasizes that rusting involves another redox reaction, and that iron is going to act as a cathode and an anode in the rusting process. So you're going to have Fe2 plus ions form at the anodic region here, and of course they're going to be dispersed through water and act with oxygen to form rust. Okay, and this is going to verify fact 3 that Mifune has stated earlier. Now, rust is Fe2O3, which is going to be hydrated with a variable number of water molecules. From our previous understanding with Mifune and this graphic here, we know that this rusting process is happening away from the pit, which again is going to verify fact number 3 from what Mifune had discussed earlier. Now, this entire process of the iron forming with the water, of course, the electrons moving through to again produce rust, is going to be incidental. And the primary damage is going to be the loss of iron, weakening the object's strength. Now, the overall reaction for this rusting process is going to be, of course, us taking two half reactions. So the first half reaction is going to be that at the anodic region, we're going to have our iron 2 plus that's formed from the loss of iron, loss of electrons here, mixing with oxygen in the water droplet, and of course water itself, to form rust here, which is Fe2O3, which is hydrated with a variable amount of water. And so that is how the rust is formed. And of course, you also are going to produce H+. Now, the cathode is very interesting because, as you can see, this is the previous overall reaction from the loss of iron, where you have iron and, of course, reacting with oxygen and, of course, H+ as well from the water droplet to produce Fe2 plus ions and, of course, more water. And the oxygen is coming from air. You kind of can see that the oxygen is going to be on the outside of the water droplet from this overall visual. Now, of course, to get the overall reaction, we're going to add both of our half reactions together. That means we have to get rid of species that are the same on both sides. So we can get rid of Fe2+, we can get rid of water molecules as well. And of course, we can get rid of H+, these 4 H+. But the reason why I did not take away the 4 H+ from the overall reaction, and I just kind of highlighted them in the overall reaction here, and this is overall, is because I want to explain to you that H+ is serving as a catalyst for this process. That means that rusting is faster at low pHs, or a higher concentration of H+/H3O+. And this understanding is actually going to verify fact number 4 from what Mifune was previously talking about. Another factor that can influence rusting is going to be ionic solutions. They have the ability to speed up rusting by improving conductivity between the anodic and cathodic regions. So that is actually going to verify fact number 5 from what Mifune was discussing earlier. Some examples could be the effect of ions in ocean-going vessels and areas exposed to road salts in cold climates. For example, the high ion concentration of seawater enhances the corrosion of iron in holes and anchors, which is going to illustrate again the impact of ionic solution. Now, Okisuki wants us to make a connection to the voltaic cell. First, we know that we do have an anodic and cathodic regions, which are physically separated. Then we can even make connections and go further and say that in the anodic region, iron acts as an active electrode, and in the cathodic region, it acts as an inactive electrode. We then can say that the moisture surrounding the pit is going to serve somewhat like an electrolyte and salt bridge, facilitating ion movement and maintaining solution neutrality. And then finally, we can also say that the metal acts as a natural conductor, enabling the flow of electrons through an internal circuit, leading to the internal flow of electrical energy that contributes to the corrosion process. Okisuki then lets us know that Mifune is ready to provide us with the last lesson. Let's go. Mifune has returned and wants to emphasize that although corrosion is not a useful spontaneous electrochemical process, the hidden corrosion village has taken every precaution to protect against the corrosion of iron. So to prevent against corrosion, the idea is to eliminate corrosive factors. So that means when you are adding road salt, you want to make sure you wash off the road salt from vehicle bodies to remove ions, which in turn is going to decrease the conductivity at those electrodes. You also can end up painting objects to keep out oxygen and moisture. You can also plate chromium on fixtures, or which is called bluing, to create a protective coating of magnetite on the surface. All of these are going to help, of course, decrease the corrosive ability. From trying to find ways to prevent corrosion, we see a pattern. Corrosion is going to increase when iron behaves more like the anode. In order for that to happen, it has to come in contact with a less active metal, something that is a weaker reducing agent, something like copper, for example. That is going to allow iron to become the anode, and of course, corrosion is going to occur more rapidly. This, in turn, is going to verify fact number 6 that Mifune had presented earlier. Now, to protect against this happening, we can use non-conducting spacers to prevent direct contact between iron and the less active material. And it's essential to know that while iron serves as both the anode and the cathode in the rusting process, it is only consumed or at the anode. And this is highlighting a crucial aspect of the corrosion mechanism. So from this understanding, corrosion is going to increase when iron behaves more like the anode. So of course, an opposite, when iron is going to make contact with the more active metal, which is more of a stronger reducing agent like zinc, iron becomes the cathode. And that means iron is going to remain intact while the more active metal acts as the sacrificial anode. An example will be the process of galvanizing, which is going to be coating iron with a sacrificial layer of zinc. So therefore, zinc is going to be oxidized instead of iron, protecting against corrosion. With this same understanding, you also can create sacrificial anodes that can be placed underwater and underground to protect iron and steel pipes, tanks, and structures. So for example, here we have an iron pipe, and then we're going to add a sacrificial anode here, which is a magnesium rod that's going to be, again, losing its own electrons and allowing iron to act as a cathode and stay intact for as long as possible. Another commonly used sacrificial anode would be like aluminum. And so the idea is that, again, you're going to be using these anodes to, again, protect against the iron pipe or steel pipe or whatever you're going to be using. You also can have like adherent oxide coatings. So you can put like magnesium and aluminum into a coating to slow the corrosion of the iron or steel as well. Mifune then tells us this is all the information he has. We thank him for his time and head back to the hidden chemistry village. We meet Kakashi Sensei at the gates. See you there, folks.